Hi, my name is Peter Sharp, and along with co-authors Demet Ulker and Mark Drela from MIT Aeroastra, we'll be presenting on Tailerons for aeroelastic stability and control of flexible wings. In this talk, we'll be referencing Dawn 1, which you see on the right, which is a high-altitude, long-endurance aircraft. Design drivers for this class of aircraft typically drive you towards extremely high aspect ratio, slender wings. You're also typically strongly power constrained, and because the power scales superlinearly with weight, you get very flexible, lightweight structures. Historically, the biggest failure mode of such aircraft has been aerostructural failures. So we aim to mitigate that with a series of techniques based on a new concept called Tailerons. When we say aerostructural failure, there are really three failure modes that we're concerned about: torsional divergence, bending torsion flutter, and control reversal. All three of these modes can be suppressed by increasing the wing torsional stiffness. Of course, this also invariably increases the wing structural weight, so suppressing these phenomena with lower weight strategies is highly desirable. To achieve this, we introduce the concept of Tailerons, which are small, all-moving actuated aerodynamic surfaces attached to booms that protrude aft from the outboard sections of the wing. They provide three main functions. First, they suppress torsional divergence by neutralizing the wing's pitching moment. Secondly, they replace ailerons for roll control by twisting the wing, essentially wing warping. Interestingly, this avoids control reversal that plagues conventional ailerons because you're effectively always operating in a fully reversed condition. Thirdly, they add considerable pitch damping because of the relatively long moment arms. Interestingly, the added structural mass of a taileron and its boom is actually minimal. So for example, in the Dawn 1 airplane as built, the taileron and boom subassembly represents less than 3% of the overall wing weight, not to mention the airplane weight. The weight gain of adding tailerons is comparable to, and sometimes even less than the weight gain from adding similarly sized ailerons, because the increased structure in the wing for the ailerons to carry the hinge loads is less efficient than the direct transfer of the loads that can be accomplished through a dedicated boom. To illustrate the second point about how tailerons can control a wing via warping, we show two cases, one where the airplane is turning left and another one it's turning right. These two cases are computationally simulated. Here on the left here, a taileron on the right side of the airplane is actually creating a downforce, which twists up the wing, increasing the lift coefficient on the right side of the wing, ultimately resulting in a turn to the left. The first main contribution of this paper is developing 2D theory to rapidly analyze taileron configurations. To do that, we first split the wing into an inner wing and an outer wing, where the outer wing is here shaded in gray. We focus on that outer wing, and we model it with an effective heave and twisting stiffness that's determined by the inner wing properties. We set up our aeroelastic problem as shown in this figure. This is detailed more in the paper, but essentially we're parameterizing it as a dynamic problem with heaving and pitching as some function of time, with linear effective stiffnesses to model structures. In general, the aerodynamic loads that you set up are about what you'd expect from aeroelastic theory. There's a circulatory component, LC, the lift, MC, the circulatory moment, as well as the non-circulatory components, LA and MA, which account for essentially the apparent mass, or most of the unsteady effect here that you're seeing. Okay, so the 2D theory is developed in much more exhaustive detail in the paper, but let's get to the main findings. Okay, so divergence, flutter, and reversal can all be modeled with this 2D theory. Let's first start with divergence. So one interesting finding is that taileron wings can essentially be made immune to torsional divergence if properly sized. We derive an inequality here, which gives when taileron wings will be immune to divergence. This right-hand side here is relatively constant. This middle term that we've highlighted, the xref over cw, is the shear center offset. That's also relatively constant. But the interesting thing is that left-hand side term, xt over cw, is essentially the non-dimensional length of the taileron arm. And this can easily be made much, much larger than the shear center offset. So if appropriately sized, a taileron wing will always be immune to divergence here. The second failure mode, flutter, can also be accurately modeled with this 2D theory by extending it with a simple harmonic analysis. So first we assume a prescribed harmonic motion here. We add Theodorsson lag functions and a series gust function to account for the unsteady effects here. And then we can predict flutter accurately using a standard VG method. So basically that looks like setting up a heave torsion eigenvalue problem with some unknown structural damping G, and then essentially sweeping over airspeeds to figure out at what airspeed does that required damping become positive. We can also use the 2D theory here to yield control reversal estimates. So in the chart on the right, we're essentially plotting the roll control power as a function of the normalized airspeed. In the aileron cases, which are shown in red and orange, the control power actually decreases with increasing airspeed because of this reversal phenomenon. For the taileron case, however, shown in the blue lines, the control power actually increases with increasing airspeed because you become even more reversed. You're deliberately operating in this control reversed case. So a taileron wing needs less than 1/4 the torsional stiffness of an aileron wing, which ultimately saves lots of wing weight. The second main contribution of the paper is validating this typical section 2D analysis with full aircraft simulation. This simulation is conducted in ASWing, which is a computational aeroelasticity tool. Here we take the representative case of the Dawn 1 solar aircraft. We give it a prescribed Taileron doublet maneuver that lasts approximately 10 seconds. Control effectiveness is computationally demonstrated, as shown in the pictures below, by the wing warping. It's also validated by the heading change that's achieved of approximately 12 degrees over 10 seconds. Another interesting result of the full aircraft analysis is the validation of the reversal speed. Using the typical section 2D analysis, we can compute the reversal speed at about 6.23 meters per second for the Dawn 1 aircraft, using the criterion set in the left side of the screen. On the other hand, with the full aircraft analysis, we can computationally simulate the reversal speed, and we find it equal to about 7.7 meters per second. This is about a 19% discrepancy between the two, which is reasonably small in consideration of the many assumptions weighed. Thus, the typical section analysis is clearly useful for understanding and estimating the basic principles of Taileron control at a fraction of the computational cost of full aircraft simulation. The third and final section of this paper broadens these findings and attempts to make them most valuable for aircraft designers. In particular, they attempt to answer the question, as a function of high-level aircraft design variables, where do Tailerons offer the most mass reduction? What kinds of airplanes should they be considered for? So to answer this question, we consider these two high-level aircraft design inputs, wingspan and aircraft gross mass, the M total. Starting with this high-level set of inputs, we then make some additional planform assumptions about the aspect ratio, lift coefficient, and an air density corresponding to 65,000 feet. This lets us compute the cruise airspeed. For example, for the Dawn 1 aircraft, we have a span of about 27 meters, a total mass of about 200 kilograms, and a true airspeed of about 43 meters per second. For the wing primary structure, we then assume a thin-walled tube spar construction, which is the prevailing choice for ultra-low wing loading, high-span aircraft, where the spars are primarily torsion-sized here. We make some additional assumptions about the size of the spar as well as the airfoil properties, and we assume that this tube spar is made of high-modulus carbon fiber construction. This tube spar is assumed to consist of two parts, both of carbon fiber composite. The first is a torsion material layer, which is a plus-minus 45-degree layup which wraps the entire circumference of the tube spar. The second part is the bending material, which is a unidirectional, span-aligned layup that's only applied to the top and bottom of the tube spar, essentially cap strips. Another part of the spar is an optional leading edge ballast weight, which can suppress bending torsion flutter in certain rare cases. These three parameters, the torsion material thickness, the bending material thickness, as well as that optional leading edge ballast, are determined by result of a spar design subproblem, an optimization problem of sorts. The goal here is to minimize the total mass of the primary structure, the spar, plus that leading edge ballast, subject to a variety of constraints which are detailed in the paper, but generally implemented using the general 2D sectional analysis that we presented earlier in this work. Based on these results, we can compute the combined spar and ballast mass for an aileron wing as well as a Taileron wing as a function of our two high-level aircraft design inputs. As one might expect, these roughly follow a power law with respect to both inputs. What this chart doesn't fully show, though, is the fact that a Taileron wing weighs less than an aileron wing at every single tested point in this aircraft design space. To show the mass savings of a Taileron wing with respect to an aileron wing more closely, we can plot that mass savings as a function of wingspan and aircraft gross mass here. As we can see, the mass savings increase generally with the gross mass of the aircraft. Perhaps a more relevant way to visualize this data set here is to look at it as a fraction of the aircraft gross mass. As we can see at the lower span end of the spectrum, the mass savings of using Tailerons versus ailerons are there, but not huge, on the order of a fraction of a percent. However, for larger aircraft, these mass savings quickly grow to be substantial, reaching in excess of 6% at the largest aircraft size scales. For a solar HAL aircraft or another lightweight aircraft where payload mass fractions are typically on the order of 5%, this would more than double the payload capability by freeing up 5%, 6% of the aircraft gross mass. So this generally presents a significant potential for future lightweight aircraft design. To summarize, Tailerons allow suppression of dangerous aerodynamic phenomena common to lightweight flexible wings, and often achieve this with significant mass savings over conventional solutions. 2D theory is developed to quickly assess performance. These key results are validated with full aircraft studies. And finally, a parameter sweep is conducted to aid designers in assessing the relative benefits of Tailerons. Thank you.